Hello friends, here the operating system class. Today we learn classical problem of the synchronization. There are three types of classical problem of synchronization. First one is producer-consumer, which is also called bounded buffer problem. The second one is reader-writer, and the third is dining philosopher problem. So in the first bounded buffer problem, here the complete array of bounded buffer with the capacity of n element. Okay, here the array of capacity n minus 1. Here the capacity of n elements array whose indexing start from 0 and end element is n minus 1. So in a bounded buffer problem, here the bounded buffer array which is shared with the multiple producer and multiple consumer. Producer is used to insert the value of the producer, insert value in the array, and the consumer consume the value of the arrays. If the array is become full, then the producer must be blocked. If the array become full, then the producer must be blocked because the buffer is full and no another insertion of the value is allowed. So in other case, if the array is empty, the consumer must be blocked, because if the array is empty, no any consumer can consume the value of the array because the array is already empty. So here in case of array is empty, consumer is blocked. If the array is full, producer is blocked. Producer is blocked because no way another one value can be inserted into the array buffer because the array is already full. So no further values are permitted to add. In case of empty and consumer, if the array is empty, no any consumer is allowed to consume the value of the array because the array is empty. So here the three variables called mutex, full and empty. Mutex binary semaphore to take the value of here the three variables called mutex, full and empty. Mutex is a binary semaphore which indicate the bounded buffer is locked or not. In case of full counting, it is a counting semaphore which denotes how many slots are occupied. And the third variable is empty. Empty is also a counting semaphore to denote the number of empty slots. It denotes empty denotes empty slots, full denote occupied of slots, and mutex denote is buffer is locked or not. Here the initialization, the mutex 1 means buffer is not locked. Full 0 means there are 0 elements in the array. Empty means how many elements are blanked, how many slots are free. So there n slots are free. Now the producer and consumer case. In producer case, so in case of producer, there is a wait signal. Decrement the value by 1. So in case of producer, empty's value is n, so it decreases by n minus 1. Value become n minus 1. Because the producer want to fill one slot, so now the empty slot become n minus 1. So here n minus 1. Now the wait signal check the mutex. Mutex means yes, buffer or not. If buffer is locked, no one can. So if buffer is locked, producer don't want to add any value into buffer. But here mutex is 1. So when 1 is applied here, 1, so value decrement by minus 1. So the value becomes 0. and the producer comes into the array buffer. It insert the value into the array buffer and then signal the mutex. Signal the mutex means increase the mutex by 1. So the mutex become again 1. Then signal the full. To signal the full, signal become 1. The fulls become 1 because there is 0 elements. Now there is 1 element in the array buffer. Okay. Now in case of consumer wait full. Check full. Full means how many elements in the array buffer. So there is a 1 element in the array buffer. So consumer can consume the value. So the full become 0 now. Full become 0 after wait function. Now check the mutex. Mutex means is array buffer logged or not. So when you check the mutex value is 1. 1 means that array buffer is not logged. So now the mutex become 0 after wait function. Now the consumer is in array buffer, bounded array buffer, and you want to perform the action to remove the items from the array buffer. So it remove 1 items from the array buffer and signal the mutex. When you give the signal to mutex, signal increase the value by 1. So now the mutex become 1. And signal the empty increase it by 1. So the empty become n. Means that now after adding one element into the array buffer, and consumer can consume 1 element from the array buffer. So now the state comes mutex 1, full 0 means number of elements 0 and number of slots empty n. Same initial condition met here. Now the second problem is reader-writer problem. In reader-writer problem, a file is shared between the multiple readers and the writers. So okay, multiple readers and the writers. What the condition is for a reader-writer problem? Reader-writer problem is the currently anyone is writing the file. If anyone is writing the file, then reading is not allowed and writing is not allowed. But when anyone is reading the files, then at that time reading is allowed, but writing is not allowed. These are the reader-writer problem. When anyone is writing in the file, then reading writing both are blocked. But when anyone is reading the file, then reading are allowed, but writing are not allowed at that time. Same things written in the statement form. If the writer is accessing the files, then all other readers and writers are blocked. When the writer are accessing the file, the reader writer are both blocked. If any reader is reading, then the other reader can, but writer are blocked. Readers can but writer are blocked. So there are 3 variables: mutex, write and read count. The value of mutex. Here the mutex is a binary semaphore to provide mutual exclusion. Writer, binary semaphore to restrict readers and writers to writing is going on. Hello. So here the mutex is a binary semaphore to provide mutual exclusion, and write is also a binary semaphore to restrict writers if the writing is going on. WRT means their writing is performing. A read count means a reading is performing. And mutex is to check or log a reading or writing. Okay, to provide the mutual exclusion. Here initialization, here the mutex is 1, write is 1 and count is 0, means readers are 0, writers are 1, and mutex means 1 means open. Yes, reading is allowed. Now when the writer comes, wait WRT, wait function decrement the write. So wait, the write becomes 0 now. write becomes 0 and writer is in performing writing. Writer is performing writing here, and the WRT is 0. Now at that time, if the reader comes, wait mutex value is 1. Now wait, decrement the value of mutex by 1, so it becomes 0. If and read count plus read count plus increment the read count with number of readers 1. If the read count 1 yes, okay, then check the condition, wait WRT is 0, so here it is stuck into the loop. It is stuck into the loop because the value of VRT is 0, so it is stuck into the loop. Here means if any writer is writing in the file or anything, the reader will stuck, not permitted to access the file. And if another writer is trying to access the files, then what happens? Wait WRT is 0. Then again writer is stuck into the loop. So reader and writers are not allowed if anyone is writing the file. Now in another case, when reader is reading the file, okay, await mutex become 0. Now the read count increase by 1. If the read count is 1, wait WRT. Now WRT is 1. Now it becomes 0. Condition true. It comes out of the loop and do the signal mutex 1. Wait signal mutex 1. Now it permitted. Now it open the. Now it's open the file to read. So it do the mutex 1. Now it performing reading. Okay. After performing reading, it again decrement the value of mutex by 0. Okay. Then read count number of readers become 1. So number of readers become 0. And if the read count is equal to 0, then signal WRT becomes 1. Give the permit to write. Now he gives the permission to write because he is going out of the reading section. He is not reading now, so it gives permitted to write into the file. Now the signal the mutex become 1. Same the initial conditions met. Now if another case, check the another case. When one reader is reading, chalo, wait mutex become 0, reader count 1, and if reader count is 1, wait WRT become 0. WRT become 0 and signal become mutex. Signal create mutex means 1. Now the reader perform reading. Perform reading means any one reader is reading the file. Now if the another reader comes to read the file, then it is allowed or not? Or other writers want to try to write the file, is it allowed or not? If any writer comes, then what happened? Writer wait WRT is 0. WRT is 0, therefore writer is stuck into the loop. These writers are not allowed when any reader is reading the file. In case of reader, is any readers allowed or not? So the wait mutex becomes 0. Now it create wait mutex 0. Read count plus means 2. And wait, check the condition of wait RT. Here the read count is equal to 1. No, read count is not equal to 1. It is become 2. So it can't enter this loop if condition and go to signal signal mutex. Signal mutex. Mutex become 1 now and performing the reading. Here, 2 readers are together performing reading. Here the read counter is 2. Reader counter is 2. Mutex check the condition. Yes, files are able to read. Files are not blocked. And writers are blocked here. Writer's value is 0. Okay. Now here the third problem, dining philosopher problem. In dining philosopher problem, if there is a k philosopher seated in around the circular table. Okay, there is a k means it's a 4 philosopher sitting in the table. There are 1 chopstick between each philosopher. Each philosopher between there is 1 chopstick. A philosopher may eat if he can pick up to 2 chopsticks adjacent to him. The philosopher can eat the food. Okay, here the plate, and here the philosopher. These are the philosopher, and each philosopher have there is 1 chopstick between each philosopher. Here 2 philosopher, 2 into there is 1 chopstick, and the philosopher may eat if he can pick 2 chopsticks. Each philosopher can eat the food with 2 chopsticks if he pick 2 chopsticks. So here the philosopher can eat the food with 2 chopsticks only, not single chopstick. But the condition is that if 1 philosopher can pick the chopstick, and this philosopher pick this chopstick, and this philosopher pick this adjacent chopstick, and this philosopher pick this chopstick. Now each philosopher has 1 chopstick, but he can eat the food with the 2 chopsticks, not 1 chopstick. 1 chopstick. Now here deadlock occur. Means no any philosopher will eat the food because they have only single chopstick. But condition is that the philosopher can eat the food only when they have 2 chopsticks. When they have only 2 chopsticks, but here they have only single chopstick. So here the semaphore. So here the code for the conditions. So here how the philosopher will eat the food if they have only single chopstick. The condition is that they can eat the food with 2 chopsticks only. So here there are 3 conditions happens to avoid the deadlock. Here the deadlock occurs. So avoid deadlock there must be 3 conditions. There is 3 conditions available here. There should be at most k-1 philosopher on the table. K-1 philosopher in the table. If we remove 1 philosopher here, now this philosopher have 2 chopsticks because here there is no philosopher. So this philosopher can take both chopstick and eat the food. After eating the food, they release the chopstick, and now this philosopher will take this chopstick. They have now both 2 chopsticks. They can eat food and then release the chopstick. Now this philosopher will take this chopstick and eat the food. Now the deadlock removed. Now the second condition is that a philosopher should only be allowed to pick their chopstick if both are available at the same time. Now in second condition says condition to avoid deadlock is that the philosopher can pick the chopstick if both chopsticks are available. Okay, here in condition first, here both chopsticks are available. Now this philosopher will pick its chopstick. Now here this philosopher has two available chopstick. Now he can condition, what condition? The philosopher can pick the chopstick if both chopsticks options are available. Then he can pick its chopstick. Now this philosopher two chopstick options are available, so he can pick its chopstick. Now here this philosopher can pick the chopstick if both chopsticks are available. Here both chopsticks are available, so he can pick its chopstick. But in case of here fourth one, only one options are available, so he can't pick any chopstick. If he can't pick any chopstick, then this philosopher will pick these two chopstick and eat food and release this chopstick. After releasing this chopsticks, this philosopher will access these two chopstick and eat food. After this taking food, it releases chopstick, and now this philosopher will take both chopstick and eat the food and release chopstick. Now all three have taken the food. Now after releasing this chopstick, and this chopstick is already released by the philosopher, so now the two chopsticks are available for this last philosopher, so this can eat food with two chopsticks. So deadlock condition removed, deadlock avoided. Here now the third problem, third condition to avoid deadlock is here. Here the third condition is that if one philosopher will pick the left first then right. If one philosopher will pick left chopstick first then right, but other is first right then left. One philosopher will pick left chopstick then right, and another philosopher will first pick right then left. Okay, so here the first philosopher first pick left then right, but another philosopher first pick right then left. The right is available then pick, but left is not available. So here this philosopher will pick right, left is not available. This philosopher will pick right is not available, so he picked not anything. He picked not any chopstick. Now this philosopher have two chopstick. It eat the food and release chopstick. After releasing, this philosopher will pick this chopstick. Now they have two chopstick. Eat the food and release the chopstick. After releasing chopstick, this philosopher will get the chopstick, eat the food and release it. After releasing this chopstick and this chopstick, this philosopher will pick this, then this, and first right, then left, and take the food. Now three cases are explained how the philosopher dining problems is avoided by these three conditions. Okay, thank you.